let's finish up chapter 5 with section 5.6, complex zeros and the fundamental theorem of algebra. So, complex zeros. When you have a factor, let's say we factored a problem, we ended up with x minus 2, and then we ended up with x squared plus 9. Alright, so clearly here there are three zeros, x to the first and x squared, right? So this was an x cubed problem to begin with. So there's three zeros. One of them is x equals 2, so we have a real zero. But then the other one, if we were to solve for the zeros here, we would say x squared equals negative 9, and we would get x equals plus or minus square root of negative 9. That's an imaginary number. So we end up with imaginary solutions here, and that's what we're going to talk about here in Objective 1. So the conjugate pairs theorem says if you have an imaginary solution, such as 3i, you must also have negative 3i. If we go back to that last one, because the imaginaries come from square rooting, you're always going to have a positive and a negative. So it's always going to be a plus or minus bi, some number like 5 plus or minus some number of imaginaries. All right. Now the last thing here, a polynomial of, let me get rid of that. A polynomial f of odd degree with real coefficients has at least one real zero. So since imaginaries come in pairs, if you have an odd degree, you better have one real and two imaginary. Or you could have three real, right? But you can't have two real and one imaginary because imaginaries have to come in pairs. All right, so let's use this to solve some problems. A polynomial of degree 5 whose coefficients are real numbers has the zeros negative 2. So I know we've got x plus 2. I know we've got x plus 3i, right? So find the remaining two zeros. If I know negative 3i is a zero, the other zero is positive 3i. If I know 2 plus 4i is a 0, I know that 2 minus 4i is my other 0. All right, so x equals and x equals for your remaining zeros. All right, try problem 7. Okay, now we're going to find a polynomial function if we're given the zeros. So we are told that we have a 0 at negative 2, so x plus 2. We are told we have a 0 at 1, so x minus 1. And we are told we have a 0 at x minus 4 plus I. So that parenthesis is important because it's always x minus your 0. The other one is also x minus your other 0, which will be 4 minus I, the conjugate. Be careful, it's not x plus and x minus. It's x minus the 0 and x minus the other 0. The sign change happens inside the parentheses. All right, we need to FOIL this all the way out. We're going to start by multiplying these together. We'll use the box method here. X minus 4i minus, sorry. Let me erase that. This is a 4 in there. X minus 4 minus I. And from this one here, we have x minus 4. And then negative times a negative is a plus I. And so we have in here, we have x squared, we have minus 4x, we have minus ix, we have minus 4x, we have 16, we have 4i, we have ix, we have minus 4i, and we have negative I squared. Now if you've done this right, every I should cancel out. Those cancel. Ix minus ix canceled. So we've got x squared minus 8x plus 17. 16 here plus negative I squared is negative 1. So 16 plus 1 is 17. All right, so we have those here. We also need to multiply x plus 2 and x minus 1. So that's going to be x squared plus x minus 2. And now we need to multiply these two together. So we're going to have a big polynomial. X squared minus 8x plus 17. We'll use the box method again. So So we've got x to the fourth, x cubed, negative 2x squared, negative 8x cubed, negative 8x squared, 16x, 17x squared, 17x, and negative 34. Now you'll notice if you've done this right on the diagonal, you'll have all the x's, all the x squareds, the x cubes, so it's easier to put them together. X to the fourth minus 7x cubed. How many x squareds do we have here? That's a negative 10, so plus 7x squared. We have 33x minus 34. All right, big old polynomial there. All right, we could graph this as well. Let's go over to our graphing calculator and plug this in. Let me turn off the other graphs. And so we have here x to the fourth minus 7x cubed plus 7x squared plus 33x, and finally minus 34. And let's go ahead and graph this. And that looks pretty good because we're crossing here at negative 2. Yep. And at positive 1, let me do a zoom standard so we have a little better look at the graph. Crosses at negative 2, crosses at positive 1. Can't see the top or the bottom. Let's do a zoom fit. Which one is that? I think it's 0. There it is. Let's see the top and the bottom of this graph. So it curves in and comes back up. What are we looking for? A negative 52. That looks good. And so we'll go to negative. Let's go with negative 60, a little bit smaller than that, and a positive 60. And now we should have a better look at our graph. There we go. And so you'll see in here, here's the curve for the imaginary solutions, right? It turned over on itself, but didn't cross the axis. So we didn't have any real solutions, just imaginary ones. 1, 2, real, 1, 2, imaginary. All right, take all that, put it together, try problem 17. All right, so every polynomial function with real coefficients can be uniquely factored over the real numbers into a product of linear factors and or irreducible quadratic factors. What this is saying is every polynomial function with real coefficients. Okay, so if you have nice coefficients out in front of all of these, 1 and negative 7 and 7, we can factor them down into factors of real and imaginary solutions. All right, last objective, let's find the complex zeros of a polynomial. So we're going to break this down. We're going to do this the same way we did in 5-5. We're going to take a look at our graph. So let's go back to our graphing calculator. Now I've already typed this one in my y6. Turn that graph off from the last time and turn on the new one. So I've typed this in. I'm going to go ahead and graph it. And it looks like it might cross there at negative 2. So let's give negative 2 a shot here with our synthetic. So negative 2. And we'll have a 1, a 2, a 1, a negative 8, and a negative 20. 1, negative 2, 0, 0, 1, negative 2, negative 10, and 20. And good news, it did work. And now we have this synthetic here. We'll go again because it looked like it crossed at positive 2 also. Right in here at positive 2. So we'll give that a shot. Let's bring down the 1. 2 times 1 is 2, 4, 5, 10, and 0. So there we go. So now we have x minus 2, x plus 2, and x squared plus 2x plus 5. Can you multiply to 5 and add to 2? No, you can't because we have two imaginary solutions. So we have to find the complex zeros now. All right, to do that, we're going to use the quadratic here from the imaginary quadratic. So negative b plus or minus the square root of b squared minus 4ac all over 2a. So we have negative 2 plus or minus 4 minus 20 over 2. So negative 2 plus or minus negative 16. And the square root of negative 16 is 4i all over 2. And so our imaginary complex zeros, complex is your imaginary ones, negative 1 plus or minus 2i. Alright, try problem 33, and your job here is done. Good luck with those problems. We'll go over any questions in class.